Hello! Today we are going to look at area between curves. Now there is a warm-up problem I would like you to try, so go ahead and hit pause and try that problem. Hopefully you had a chance to look at this problem. Now here's how I would go about this particular problem. I'm asking you to change my definite integral into a Riemann sum. Okay? And remember, a Riemann sum is when we take rectangles of equal width and we add them all up to estimate the area under a curve. And so what we need to find then is an expression for the width of the rectangle and the height of the rectangle, because we know to find the area of the rectangle we have to do width times height, or base times height. So I know the width of the rectangle is going to be delta x. So the first thing I'm going to find is delta x. And remember, delta x is b minus a over n. So for our particular problem, the b and the a come from the bounds of my integral. So my delta x would be 6 minus 1 over n, or 5 over n. So what I can see from that is, because my delta x is 5 over n, really the only two I'm going to consider are going to be b and d at this point. Well, then I need to go and find the height of that rectangle. And so remember, to find the height, we use the expression f of a plus delta x I. Okay, so the a is still that same a that came from my bounds of my integral. Delta x we just found, so this delta x is the same delta x that we just found, and we're substituting that into my function that was given. Well, the function that was given was something cubed. Okay, well, I notice all of them have something cubed, so really now I just need to make sure my function is correct. So the a value that I have is the a value from my lower bound, so that will be 1, plus delta x we already got was 5 over n, and then we usually use I. Now what you'll notice is that all of these limits had a k value. That's okay, just replace I with k. It's the same thing. So which one of these is this? This would be d. So d would be the limit that would be equal to that definite integral. Now, before we go on and actually look at area between the curves, I want you to think back to what we talked about, what a definite integral represented. Remember, a definite integral represents the net signed area of the region bound by the graphs of f and the x-axis. This is important. So the function and the x-axis. What we're going to do today is try to figure out how we can find the area bounded by curves, but not the net signed area, not the result of the positive and the negative added together, but we want just the total area, as if it were a geometric shape we were taking the area of. So how do I do that? Well, we're going to look at 3 different scenarios, and what we want to do is figure out what pattern we see happening with each of the shapes as we go through. So keep an eye out for patterns that you start to see happen, so we can develop a rule, if you will, to be able to find the area between curves. Let's start with this first scenario. So this first scenario is when we're given x bounds. Okay, so if we're given x bounds, we want to find the integral formula that would yield the area of the given region. And we have 2 graphs here. We have the equation y equals x squared plus x plus 2. So that's done in green. Let me just highlight it a little bit better. So that's this area. And then we have our y equals negative x. So y equals negative x is obviously this blue line right here. And then we have our x and bounds from 0 to 2. Okay, well, if we are trying to find the area under the curve for this green function, this y equals x squared plus x plus 2, when I find that area under the curve, remember, this gives me the area of the shape between the x-axis and the function. So my area under this curve would be this particular area. Could I write an integral that represents that? Sure. I could write the integral from 0 to 2, because those are my upper and lower bounds, of x squared plus x plus 2, I may throw parentheses around that, dx. So if I wanted to find just that green area, I could do that. All right, what if I want to talk about the area under the curve for the second function, the y equals negative x, that blue function? Well, the area under that curve is actually going to be this triangle between the curve and the x-axis. And when I find that area, I would get 0 to 2 of negative x dx. Now here's the problem. What would this area yield? If we did this, what would this area be? Is it going to show up as a positive or a negative? Well, it's going to be a negative because it's below the x-axis. So we need to think about how we can combine these two. Is there a way to combine these two and write it as one integral? Is there a way to do that? Also, along that same line, how do we make this positive? Okay, let's think about that. If I want to combine these as one integral, but I want to make that blue area, the from 0 to 2 of negative x dx positive, how do I do that? Well, I'm going to subtract the two. So I can combine this to be the area under the curve from 0 to 2 of x squared plus x plus 2 minus negative x. That will turn that area positive. And if I take the integral of all of that with respect to dx, or with respect to x rather, then I can find the total area. So let's try it. If I want to evaluate this, I may simplify it first. So x squared plus x plus 2 plus x would give me x squared plus 2x plus 2. And when I take the antiderivative, we'd get x cubed over 3 plus x squared plus 2x evaluated from 0 to 2. Plugging in 2 and 0 using the fundamental theorem of calculus, plugging in 2, we would get 8 over 3 plus 4 minus, well, all of that would be 0. So we get 8/3 plus 12. Oh my goodness, we don't either. We get 8/3 plus 8. So we'd get 8/3 plus 24/3, which is going to give me a total of 32/3 would be my area bound by those two graphs and those two x values. Okay, well, let's look at another one. I'm going to scroll up. Scenario number 2. Actually, maybe leave that up just a little bit. Scenario number 2, I'm going to go back and look at these two graphs again. We have y equals 6 minus x squared, so this is the graph in green. And then we have y equals negative x again. So y equals negative x is that, oops, we'll pretend that was straight, line that looks like this. But it didn't give me any values of x that I need to be concerned about. And it's going to be really hard to write the area under the curve because the area for the green that I would need to have would be this total area. So starting where they here, right here where they intersect, let's do that again. Starting right here where they intersect to right here, I would need to find this area and then this area, and then I'm not sure what to do with right here. I'm not even sure what to do with all of that. So what do you think I'm going to do? Well, we know area under the curve is really just made up of a bunch of rectangles if we use that idea of Riemann sums. So let's look at what a rectangle under here might look like. Let's say I were to draw a rectangle here, a skinny little rectangle, and I were to draw lots of those. Remember, the width of the rectangle here is going to be delta x or dx, right? Now, what is the height going to be? How do I determine the height? Well, it starts here at this y value and ends here at this y value. Could I take and subtract the two y's? So if I look at the height of this shape, do you agree that I could take the value I get at 6 minus x squared and take away the value that I got at negative x? So let's put that in integral form. Do you agree that I could do 6 minus x squared minus negative x, and that would be the height? And then the width of the rectangle would be dx. Okay, so if I add up all of these rectangles that are connected in here, could I eventually get them? Remember, that's what integral means, is the sum. But what am I missing? What do I need here? I need to figure out what are my bounds. What are my bounds of integration? Because I can't do this without my bounds. Well, my bounds of integration start where they connect right here and end where they connect right here. So what am I actually looking for? I'm looking for their intersection. So let's do 6 minus x squared equals negative x. So rewriting this, I would get x squared minus x minus 6 equals 0, which means x minus 3x plus 2 equals 0. So x equals 3 or negative 2. 3 or negative 2. So those would be my bounds. I'm going to start at negative 2 and end at 3, and I'm going to subtract 6 minus x squared plus x. So let's do 6 minus x squared plus x dx. All right, well, let's evaluate this. If I evaluate this, I'm going to get negative x cubed over 3 plus x squared over 2 plus 6x evaluated from negative 2 to 3. All right, plugging in 3, we would get negative 27 over 3 plus 9 over 2 plus 18 minus, let's plug in negative 2. So I'd have negative 8, so 8 over 3 plus 4 over 2 plus a negative 12. Maybe I'll just write minus 12. Okay, so negative 9 plus 9 halves plus 18, so positive 9, minus 8 thirds, minus 2, plus 12. So it looks like I get 19 plus 9 halves plus, minus 8 thirds. So if my denominator's 6, denominator's 6. So 19 times 6, why can I not do that in my head? 19 times 6, 114. So we'd get 114 plus 27. 114 plus 27, 141 minus 16. So 141 minus 16 be 125 over 6. Okay, so that's scenario number 2. Now, do you see a pattern at all? Do you see a pattern emerging with how we're writing our integrals? Not the separate integrals that we were looking at, but the final before we actually start solving. So do you see any pattern with how we are writing the 2 that I'm boxing right now? Oh, maybe let's go back and box this one. Do you see any pattern? Maybe look at those, which graphs we are subtracting from which one. Do you see anything? Let's look at another example. Okay, so we are going to look at this last scenario when there's multiple regions bounded by the graph. multiple regions bounded by the graph. Unfortunately, this one traced black, so you can't see the two colors. There are green. So we'll sketch that in green, and then we'll sketch this one in blue. Okay, this kind of has a combination of the last scenario that we looked at, as well as one other piece. Okay, let's call this region 1 and this region 2. Do you think that has anything to do with it? Well, let's start with region 1. If we start with region 1, the rectangles that I'm going to draw the width would still be dx. What would the height be of that rectangle? What's the height? Well, the highest y value starts at the green curve and ends at the blue curve. We'll pretend that touches, go with it. So that's the height. Now, when I look at this, how would I find that? Well, I would take this green equation, 2x cubed minus x squared minus 14x, and I would subtract from it the blue equation of 4x minus x squared. Okay, so can you agree that if we look at region 1, we'll just call this region 1, that the area under that curve starts at 2x cubed minus x squared minus 14x and then goes down to 4x minus x squared? Okay. What am I missing? Well, I'm missing my bounds of integration. What is this point right here? What is this point right here? Well, how did we do that last time? To find these bounds of integration, we've set the two equations equal. So we would say 2x cubed minus x squared minus 14x equals 4x minus x squared. If I go and combine like terms, I get 2x cubed minus 18x equals 0. So we get 2x times x squared minus 9 equals 0. So we get x equals 0 and x equals plus or minus 3. So my bounds of integration here are going to go from negative 3 to 0. And that would give me that first region. Now, is that going to be the same for region number 2? Can I set up the same integral just with different bounds? Well, let's think about that height of that rectangle. If we look at the height of the rectangle, how would I calculate that? Well, the height of this rectangle, I would need to take my blue curve, 4x minus x squared, and subtract from it the height of my green curve, which would be 2x cubed minus x squared minus 14x. We're going to pretend I can fit a dx in there. And my bounds of integration here would be from 0 to 3. So if I add these two regions together, I should get the total area under the curve. So let's simplify it just a little bit. If I evaluate this from negative 3 to 0 of 2x cubed minus 18x dx, and add that to 0 to 3 of 18x minus 2x cubed, I should get the region, the total region, region 1 plus region 2. So what I want you to do now is take a second and try this in your calculator. See if you can figure out, and do it in your calculator. You can either do it under the graph menu or you can do it in the math menu on the main screen, Math 9. So try this and see what you get. Okay, hopefully you got 81. So do you see a pattern again? If you look at this, for region 1, we took the green curve and subtracted the blue curve. For region 2, we took the blue curve and subtracted the green curve. Could you generalize that? If we're trying to find the area between two graphs, and we've looked at 3 scenarios, In each of the three scenarios, what did we do to write an integral expression? Well, if we want to generalize this, we can look at some examples here. That the region between two curves is going to be the top curve, whatever that top curve is, minus the bottom curve in between our two bounds that we're looking for, okay? As long as it's a function of x. Now, we're going to look at a couple of examples when we come back from break of functions that are in terms of y. But before we do that, I want to just give you a taste of what it looks like. Notice on the x functions, I'm subtracting the higher y value function minus the lower y value function. So if it's a function with respect to x, I'm going to subtract the higher x value minus the lower x value, okay? The right curve minus the left curve. So for functions of y. All right, you ready to put it all together and try an example? And we're actually going to use our calculator. So have your calculator handy. And I actually got an emulator, which I mentioned in the next video, so you'll see that. Okay, let's try it. I want to find the total area of the regions located between the two curves as they're shown. And we're going to use a calculator. So how do I set up my integrals? Before we do anything else, let's set up the idea of the integrals so then we know how to use the calculator. Okay, well, let's start with this left region. We're going to call this one region 1. And we'll call this one region 2. This was an R. Region 1 and region 2. If I were to set up region 1's integral, maybe I don't know my bounds just yet. I don't, because I need to find them. But I know that this integral is going to go from the x cubed function, the upper function. So I'm going to take x cubed minus x squared, and I'm going to subtract from it the negative x squared plus 4.1x. Can we agree with that for region 1? Now, I don't want you to type anything in your calculator just yet. I'm going to show you how I want you to put this in. And then I'm going to add to it the area under the curve of region 2. Well, region 2, which function is the higher function? Well, in this case, that's the x squared plus 4.1x. So negative x squared plus 4.1x. I'm going to subtract from that the x cubed minus x squared. Okay, well, this is messy. I forgot the dx's on both. This is messy. So do you agree that I'm going to take my first function, we'll call it y1, and I'm going to subtract y2. And the second one, I'm going to do function y2 and subtract y1. Okay, so we're going to, in our calculator, under our graph menu, we're going to go to y equals, and in y1, I'm going to put in x cubed minus x squared, and in y2, I'm going to put in negative x squared plus 4.1x. Okay, so here's how we use the calculator. And there's a reason I don't put myself on screen very often when recording videos. You'll see why. Okay, so here we go. All right, I want to look at graphing this via the graphing calculator, and I have an emulator, at least for a little bit. So the first thing we would do with this one is put it into y equals. And I just want to walk you through just some ideas to be able to put this into your calculator better and use it better on AP test. Got to talk kind of fast because it's got to be 5 minutes. So the first thing that I'm going to do is I am going to graph these two equations. And while they're not beautiful, I could probably zoom in. What I actually am concerned about is finding their intersection point. So I'm going to do second calculate. And number 5, I'm going to go to intersect. And I am going to go down to approximately where that first curve intersects and hit enter. Hit enter for the second curve and let it guess. And it gives me my intersection point of negative 2.02. Okay, but it's calling it x. So watch what happens when I quit. When I quit out of this graph, if I go to alpha and go to x, what's going to happen is it's going to bring up that x value. Now it only stores the most recent x value that we just got. So what I'm going to do now is I'm going to store this in an alphabet letter. So I'm going to call it A, and it'll say that I stored it in A. Now I'm going to go back to my graph and I'm going to do second calculate intersect again. And I'm going to find this other intersection point because I'm pretty sure that one is 0 and I could check it on the table. I know it's 0. So let's do my first curve. Let's get it close to that third intersection point there. Hit enter, enter, enter. And it gives me my other intersection point. So when I quit, what I'm going to do is I am going to bring up alpha x. And if I hit enter, it's going to bring up that same value. So I'm just going to hit store and store it in alpha b. Then I have my endpoints already stored. I have my first equation in y1 and my second one in y2. Now what I'm going to do is I'm going to go and I'm going to calculate under math, number 9. I'm going to do the integral. And this time I'm going to go from a to 0. So I'm going to recall alpha a. And then I don't have to type. It's the exact bound. I don't have to worry about it. This is what we want to do for the AP test so that you're not losing decimal values. And then I'm going to do variables, y variables, function y1. And I'm going to do y1 minus y2. So variables, y variables, function, y2, and hit enter. And this is still with respect to x. And then I'm going to add it to the other region. So I'm going to choose number 9 again. This time I'm going to go from 0 and my upper bound is going to be that alpha b. And then notice again, I'm not typing decimals, but this time I'm going to do y2 minus y1. So variables, y variables, function y2 minus variables, y variables, function y1. And then I'm going to go over and choose dx. And now when I hit enter, it gives me the area of those two regions. So that's how we would use our calculator on this particular question. All right, so there is a quick example using a calculator. We've done 3 where we've done them by hand. Hopefully you now see how to find the area between curves. And now it's up to you. Now you get to try them. So we will see you in the next video when we talk a little bit more about area between curves and we'll look at some more FRQ questions. So have a great day.